We ended our discussion of the mechanism of free radical halogenation of alkanes with two questions. Why is the tertiary radical so much more stable than the secondary radical more stable than the primary radical, such that regardless of whether we're doing bromination or chlorination, we end up with a higher relative reactivity for the tertiary position? And why is bromination so much more selective than chlorination? In this video, we'll attempt to answer the first question. Recall that the relative reactivities for the different halogens for primary, secondary, and tertiary positions. For fluorine, it was in the ratio of 1 to 1.2 to 1.4. Chlorine, 1 to 4 to 5. And for bromine, 1 to 80 to 1700. So even for the highly exothermic reaction of fluorine gas, the tertiary position is favored. And for bromine, very much favored. So why is the tertiary position? What is it that causes the tertiary radical to be more stable than the secondary? We can write a radical stability series that says the tertiary is greater than the secondary, which is greater than the primary, which is much greater than the methyl radical. So let's look at the structure of these radicals. Methyl radical has a half-filled p orbital. And sp2 hybridized carbon. And thus a trigonal planar geometry. The lone electron does not count as an electron group for the purposes of VSEPR theory. The electron group requires a pair of electrons, which we have here in a carbon-hydrogen bond and two additional carbon-hydrogen bonds. So the carbocation with an empty p orbital would be sp2 hybridized and trigonal planar, whereas a carbon anion with a full load pair would be trigonal pyramidal. As a molecular geometry with the lone pair in sp3 hybrid orbital, sp3 hybridization for the electronic geometry, or tetrahedral electronic geometry, sp3 hybridization. But the lone electron doesn't do that. So the radicals are planar at the carbon where the radical exists. So now let's extend this from methyl radical to ethyl radical. I'm trying to see why this one might be more stable. We still have an electron deficient half-filled p orbital. But now adjacent to that, we don't have another planar atom. We have a tetrahedral sp3 hybridized carbon. And that means that at least one of those carbon-hydrogen sigma bonds is going to be in the same plane as the p orbital. The way I've drawn it here, this carbon-hydrogen bond is in the plane of the p orbital. And that bond is formed by overlap of an sp3 orbital on carbon and the 1s orbital on hydrogen. Pair of electrons there. Because that's in the same plane as the empty p orbital, or the half-filled p orbital, it has the same symmetry, which means that it can interact through a phenomenon called hyperconjugation. Which is defined as the donation sigma bond into an electron deficient p orbital or pi orbital to stabilize the system. No hyperconjugation is possible for the methyl radical because all three of the hydrogens lie in the nodal plane. If we take this as the y-axis and the horizontal as the x-axis, then the hydrogens all lie in the xz plane, and we have an empty py orbital that has a node in the xz plane. It's not possible for all three of these hydrogens to lie in the xz plane simultaneously. At least one of the CH bonds has to lie in the y, in this case, xy plane. A hyperconjugation interaction where this pair of electrons from the carbon-hydrogen sigma bond can help fill up the electron deficient half-filled p orbital to some extent and stabilize that radical. In truth, it isn't really one carbon-hydrogen bond that overlaps. In truth, it rotates so that one of the hydrogens is actually in the plane with the same plane as these two. It requires a molecular orbital approach. It's a little bit more difficult. So we're going to stick with this valence bond approach with this sigma bond between an sp3 carbon orbital and a 1s hydrogen orbital, donating some of its electron density into the p orbital. Sigma electron donating into an electron deficient pi system. That's hyperconjugation. If we extend it, then we change another one of these hydrogens into a CH3 group. Now have the same hyperconjugation interaction that we had with the ethyl radical, but we have an additional hyperconjugation interaction from the other carbon-hydrogen bond, sigma bond. And so now we can get stabilization from two sigma bonds donating. There are two hyperconjugation interactions. Two hyperconjugation interactions stabilize that half-filled p orbital. More than one hyperconjugation interaction, making the isopropyl radical more stable than the ethyl radical. Let's extend it one more. So now we have T-butyl radical. We have three adjacent sp3 carbon to 1s hydrogen sigma bonds. And that means we have three places where hyperconjugation can interact while stabilization. And the more hyperconjugation interactions you have, the more you are able to spread that electron deficiency over additional atoms. In the case of the methyl radical, all of that electron deficiency is localized on carbon. It is a carbon radical. For ethyl radical, we've spread that electron deficiency out over two carbons and a hydrogen. For isopropyl radical, we've now spread that electron deficiency out over three carbons and two hydrogens. And for 2-butyl radical, we've now now spread it out over 4 carbons and 3 hydrogens, so that the system as a whole is much less electron deficient, or at least the electron deficiency is less localized, and that helps. The last thing we want is localized charges, or in this case, a localized radical, but no actual charge here. We will use the same argument, this hyperconjugation concept, donation into a electron deficient p or pi orbital from an adjacent sigma bond, just to explain why a tertiary carbocation is more stable than a secondary carbocation. The secondary carbocation is more stable than the primary carbocation, etc. Because a empty p orbital is even more electron deficient than a half-filled p orbital, so you would expect the hyperconjugation to be even more important in the case of the cation. So this is donation from the sigma bond. It has to be an adjacent sigma bond. This is just with that word adjacent in there. An adjacent sigma bond into an electron deficient pi or p orbital. We'll use hyperconjugation, as I said, to explain the stability of the carbocations and also to explain the stability of the carbon-carbon double bond. It turns out that the more substituted the carbon-carbon double bond is, the more different things there are attached to the carbon-carbon double bond. The more stable the pi system. So this is a more stable molecule than if there was only 2 methyl groups or just 1 methyl group. So donation of an adjacent sigma bond into an electron deficient p, or in this case pi orbital, will stabilize the electron deficient system. And the term is called hyperconjugation. So when you don't know what you're talking about, try resonance and see if resonance helps explain it. Try sterics and see if sterics helps explain it. Or polarizability. Maybe polarizability is the reason why that phenomenon is observed. And now you have hyperconjugation. So if none of the previous 3 work,